This video is the first in a little series I'm going to do called A Practical Guide to Representation Theory. So what do I mean about practical? What I mean is this series will be focused on examples and applications of theorems. So using theorems to work out those examples. What I'm going to be less focused on in this series is providing rigorous, detailed proofs of all the theorems. Because, well, I think this is less entertaining, in part. And also, you can go and read those rigorous, detailed proofs. Now, of course, if you're reading a proof in some textbook to do with representation theory and you have a question, there's something you don't understand, of course, feel free to comment this down below and ask me about it. Maybe I'll make a video. But what I want to focus on is really a computational approach. So looking at actual examples, something we'll talk about here is the idea of character theory, and say using character theory to work out something called the character table of a group. So I want to do stuff like look at that concretely and sort of talk about strategies for actually computing that and realizing, having explicit realizations of representations. What else do I want to focus on? So, by the way, I should mention that I would also like to focus on showing you how to write some actual code. So even if you have let's even say no experience writing code in CoCalc or Sage, I want to show you how one can use things like, so here we have, for example, I've printed out the character table of a group, right? I want to show you how to use stuff like Sage to do actual practical computations with groups. So that's what we're going to focus on. So what I'm assuming here is that you already know stuff about group actions. You've maybe at least heard about representation theory before, so I'm not going to go all the way back, introduce group actions from the get-go. I do have some videos on group actions and the orbit stabilizer theorem you can check out. If you really, really want me to make some other videos about group actions more generally, I would be happy to. Just ask and let me know. But for now, let's just dive into representation theory and dive right into the examples. So what is a representation? So, well, a representation, number one, is a special case of a group action, right? So remember, a group action, there's several different definitions. And let me tell you, even though this is going to be a practical course where I'm going to be focused on computations, don't think I'm not going to be dipping into theory at all, okay? If I start talking about some theory that makes your eyes cross over, by all means, skip ahead. I won't be offended or something. But we are going to talk about some like fancy categorical stuff at some point, undoubtedly. So, a group action, we have several different definitions, right? So one of the definitions is that we have this map, right? Gx to x. Sometimes we write it with a sigma. And sometimes as a shorthand, we write g dot x for this map sigma. So definition one is, we just want to make sure that the identity element acts by the identity and that composition is respected. So if I act by h and then I act by g, that's the same as acting by their product, right? So this is definition number one. And in general, we just take x to be a set, right? But of course, it could have plenty of other structure to this set. What if we didn't just take it to be a set? For example, what if we took X to be a topological space? Or what if we took X to be, an abelian group or just any sort of group? In particular, the question is, what if we took X to be a vector space? Now, it's all well and good. I mean, in any of these cases, you could literally, because X is just a set in full generality, you could have it be any other mathematical object you wanted. That's fine. But of course, one thing that we're interested in mathematics is sort of compatible structures. It's one thing to just say, oh yeah, it's a map on some topological space, but it's another thing entirely to say that, given this element G, the map G dot, so the map given by this action, right? That's a map from X to X. And so there's maybe a little bit more going on if we demand that this map is a morphism in the category that X is in. Now, if that doesn't make sense to you, all I mean is that it's the right kind of map for the sort of structure that X has. So for example, if X were a topological space, we would want this map to be continuous. If it were an abelian group, we would want it to be an abelian group homomorphism. And if it were a vector space, we would want it to be a linear transformation. And so that's exactly what a representation is. So version 1, a representation is just an action of a group on a vector space where G dot is linear for all G, right? Okay, so how else can we express this? So let's recall the definition of a group action, right? There's another equivalent definition where a group action is equivalent to giving a homomorphism from your group G to the set of bijections on the set X. So how does one go from this sort of first definition of a group action? Well, it's fairly straightforward. All you have to do is realize that, yeah, taking this map here, or what we might call G dot, this defines a bijection from the set X to X, right? And this second condition in the group action is exactly what we need to guarantee that the map sending G to the bijection, G dot, is in fact a homomorphism from the group that you started with to the group of all bijections. And so naturally, you might consider that in other cases, right, the group SX, right, the set of all bijections of a set, that's really the set of all automorphisms, we might say, of the set, right? All the structure preserving maps of the set. And so you might naturally then wonder, well, for the more general definitions, perhaps I want to replace SX with all of those bijections that preserve the structure. So again, if X were a topological space, we would want all of those bijections which are continuous. Actually, we want something a little stronger than that. We want all homeomorphisms, but let's not worry about that. We're not talking about topology. In particular, though, since we're talking about representations, we want to deal with those maps which are linear bijections, or in other words, an isomorphism of a vector space. So equivalently, a representation of G on a vector space V is equivalent to a homomorphism from G to the group of all invertible linear transformations, right? So now we have to be careful. This could be an infinite dimensional vector space, and we will eventually see examples of that, although for the first while, we will be focused on representations of finite groups and focusing on finite dimensional vector spaces. So one thing that we often do, speaking of finite groups and finite dimensional vector spaces, what do I really mean by GLV? Well, if V is n-dimensional, then by picking a basis, we know that every linear transformation can be represented as a matrix. And so really, now I guess I haven't specified, this is a vector space over some arbitrary field. We're going to focus in on some particular fields in this series. But in general, then what is a representation of a group? Here's definition number 2, is that it's just a homomorphism from your group into n by n matrices, right? So there's definition 2. Why am I spending so many times on all these definitions? This is supposed to be a practical guide with lots of examples. Well, that's because it's going to be easier for us to construct a bunch of examples, right? Because we're going to have access to different definitions. And so those are going to give us different ways that we can express or define examples. So before we finally dip into some concrete examples, let me give you one more abstract definition. So skip ahead if you're tired of the abstractions. This will be one for the abstract people. So notice that, so if you know what a group action is, then perhaps you've seen this before, where one takes a group and forms, so I'll call it G underline. This is the one object groupoid. So you form a category with one object, just call it star, and you define the HOM set of this one object. You define it to be the group G, and you define your composition to be just multiplication in your group G. Then the data of giving a group action, this is actually equivalent to providing a functor from your one object groupoid into the category of sets. Okay. And so naturally, then you might suspect, so we already talked earlier about, well, there's all of these different kinds of group actions that we may want to take, right? We may want X to have all sorts of different structures, and we'll want to preserve those different kinds of structures. So, what would be the analog of that from this functor perspective? Well, of course, it's just that you have now this functor landing in a different category. So, if we wanted it to somehow be some topological, some continuous group action, right, we would have it land in the category of topological spaces. And perhaps unsurprisingly, if we wanted it to be a representation, we would have it land in the category of vector spaces over some field K. Okay, so that is enough for the abstract mumbling. Now that we have a whole bunch of definitions, let's go ahead and try and see if we can come up with some examples. So we want to think like a mathematician, right? What is the stupidest possible example we could construct first? So here are some questions. Can we define, are there any representations at all? And if representations do exist, do they exist for every single group? Can we always construct a representation of any group? Well, let's start with the stupidest group, right? Why would we work hard? So we'll start with the trivial group, right? This is the group. Sometimes we just write it as 0, right? It has a single element, the identity element. And we want to come up with a representation. Well, what do we need to do? There's a couple different options. So we have these different definitions where we could have the trivial group acting on a vector space from our usual definition, but we want to make sure that it acts linearly. We could also view this as providing a homomorphism from the trivial group into our into a vector space. That would also be an option for us. We could also, if we're talking about finite dimensions, view that as a homomorphism into, n by n matrices over some field. So we have a bunch of different options, right, for what vector space we're going to choose. What vector space should we choose? I mean, up to isomorphism, vector spaces are entirely determined by their dimension. So could be any natural number of dimensions. And of course, why wouldn't we just start with the easiest one, right? We're just trying to convince ourselves that these things exist in the first place. So what do I need to do? Well, according to definition 1, I need to define a group action. So let's start with the 0-dimensional space, right? So I need to find a group action of this group on this set, right? Which it contains a 0 vector and nothing else. Right? I mean, at this point, we could be working over an arbitrary field, right? It's the 0 vector. So what do I need to do? Well, I have one element in my group and I have one element in my vector space. In order to define this action, there's really only one thing to do, is I need to tell that element where to go. Well, I don't have any choice about where I'm going to send that element. Right? There's only one thing in this vector space, so I'm literally forced into this choice. So now we check our axioms of a group action. Okay, axiom 1 of group action is satisfied. Is axiom 2 of a group action satisfied? Well, What is this? It's E. We need to see is E dot zero vector equal to E times E dot zero vector. Well, E dot zero vector is the zero vector, so this just becomes E dot the zero vector. E times E is E, so this is E dot the zero vector, and yes, it's satisfied. Okay, so it's a group action. How else could I have specified this? Well, we also can just look, right, abstractly to view this as a homomorphism. We could look at V and ask, well, what are the invertible linear transformations of this vector space? Well, again, what does that mean? I'm trying to define a linear map from, my apologies. I haven't convinced you yet that this map is linear. But of course it is, right? So we're working over some arbitrary field. Let alpha be an element of that field. There's only one vector to check, right? So we go alpha scalar multiplied by this vector. So what are we trying to prove, right? Let me write things more generally. Give me just a moment here to write things more generally, right? What does it mean to be a linear transformation? Well, we can sort of write it compactly and say that for all vectors u and v, t of alpha u plus beta v is alpha t u plus beta t v. Okay, well, in this case, now let's see that t, right? V is just the zero vector, only consists of the zero vector. So in this case, the only thing that we can choose for our zero vector, for our vectors u and v, is just the zero vector. Give me a moment to write this out. Okay. And well, where does t send the zero vector? Well, it can only send it to one thing. Again, there's only one thing in this vector space. So what do we send it to? We have to send it to the zero vector. And in particular, well, I guess now I should be substituting t for the map E dot, right? I should be plugging that in here to see if it's satisfied. But we know necessarily, we've also checked that's where E dot sends the zero vector. So this is what it works out to on the right-hand side. On this side, we'll write E dot of, well, what's alpha times the zero vector? We know in any vector space that's just the zero vector. Same thing with beta times the zero vector. So over here, we're going to get, for the exact same reason, this is just the zero vector. This is just the zero vector. We add the zero vectors together. We get the zero vector. This is E dot of the zero vector, right? E dot of the zero vector. But again, E dot of the zero vector is the zero vector. So I know I'm doing way too much detail for the most trivial example, but okay, technically these are the things we need to check, right? So really this is linear. And by the way, this exact same computation, if we carry out this exact same computation, right, we find that the only linear transformation of this vector space, so GL, right, the invertible linear transformations of the zero-dimensional vector space, it really just contains one thing, and that is the zero map. So this is, now we're getting, there's too many zeros, really abusive terminology here, but sometimes we call this the zero map, right, which sends every vector to zero. And well, of course it does. So maybe I don't know. Maybe I'll call it big. Maybe I'll call it I. Maybe I'll call it I for the identity, right? It's entirely determined by this. And so what are we doing? What is in this other perspective where a representation is equivalent of going from G to GLV? What are we doing? We're giving a homomorphism from the group G, from the trivial group. So it contains this element to the identity. Well, of course, there's up to isomorphism. There's only one group with element 1, right? That's why we call it the trivial group. So I mean, you can convince yourself that this indeed defines a homomorphism of groups. Okay, so we've done step 1. We've convinced ourselves that a representation exists, and in fact, the stupidest one possible exists. So now we have a couple other questions here. What are we doing? What other representations exist? Right? Is this all? What about for other groups? So we've convinced ourselves that a representation exists. But does a representation exist for every group, right? We've used this really trivial group, so it was really easy to construct something. So again, let's return to the case of an arbitrary group. And again, we could try and take the stupid vector space, right? We could try and take the stupid vector space. And here's a little hint, like if we take the trivial vector space again, we know that this group here, GLV, right, this is isomorphic to the trivial group. We've convinced ourselves that it has just a single element. It must be the identity element. And if you're familiar with group theory, well, you know that from any group, right, there always is a homomorphism. We sometimes call this the trivial homomorphism. And again, speaking of abusive notation, we write both the trivial group as 0 and the trivial homomorphism as 0, right? So there is always a homomorphism from our group to the trivial group. But in this case, we're just imagining at this point that it is sort of our model for the trivial group that we're taking in this case is just the group with the identity, as its only the identity of the zero-dimensional vector space, right? The one linear transformation on the zero-dimensional vector space. Okay, great. So that answers the question, right? For all groups in existence, we can always construct at least one such homomorphism, right? So we can always construct at least one such representation. But what are some other representations we could construct? So notice, right, not only, so you start thinking, well, yeah, I always have the trivial map into the trivial group. But actually, between any two groups, I always have the trivial homomorphism, right? It is always true that the homomorphism, which sends every element of G to the identity element of H, this is a group homomorphism. And so in fact, if we take any vector space over any field and we consider the group of invertible linear transformations over that vector space, I can always form a homomorphism from my group G into the group of invertible linear transformations by simply sending, right, by taking the zero homomorphism. I send every G to the identity of this group, right? I send it to the identity of the group. And what is the identity of this group? I mean, it is quite literally the identity map, right? So it's the linear transformation. It's a linear transformation which sends every vector to itself. So, actually, what we have found now is that the world of representations is, in fact, quite abundant, right? We have created on every vector space. So if you give me any pair, right, any pair of a group and a vector space, I can construct a representation of that group on that vector space, right? So I can give it an action, which is linear, which is equivalent to providing a homomorphism here. By the way, one of the perspectives I haven't talked about too much yet is this third perspective, which really is not too different from the second perspective, right? It's equivalent to just choosing a basis. So what does this look like in matrices, right? So equivalently, at least when V is finite dimensional, which notice, by the way, for this construction I've talked about here, there's not even a restriction on V being finite dimensional, right? We're infinite dimensional, the craziest cardinality basis vector space. You have this whole construction works just fine. So what does this look like in terms of matrices? Well, of course, for finite dimensional vector space, this would be the same, say GLNK of just taking this the map that sends every element of your group to n by n matrices to the identity, the n by n identity matrix, right? So it's got ones on the diagonals and 0 everywhere else, right? Again, this is just a special case of using the fact that between two groups, you always have the homomorphism sending everything in your group into the identity of H. Okay. Well, so that's great, but that may seem like, well, what a chaotic zoo. I mean, there's a lot of representation. Maybe there's too many to even be useful, because I just told you that, on every vector space and every group, we can always construct a representation from that pair. So that seems like kind of a lot, no? Yeah, but I mean, we constructed pretty stupid ones, right? So the question is there something more interesting that we can come up with? Well, we turn our attention now to particular groups, right? And what is the next simplest group to look at? We sort of did this detailed investigation. Before we turn to a more detailed investigation, let's return once more to the trivial group. And we ask ourselves, for the trivial group, what other representations, how many representations could we possibly form? Well, here's the thing. We're totally fixed, right? For the trivial group, I want to send this into, I want to send this homomorphism into GLV of any vector space. But we know that every group homomorphism has to send the identity to the identity. So of course, I have no other choice for the trivial group. So in this case, for the trivial group, we've already completely classified every single representation of the trivial group, right? That's it. We're done. They're all exactly this. For every vector space, there exists one and only one representation of the trivial group on that vector space. Okay. So now let us try and stretch our minds and go to a slightly more complicated group, right? There's one group with one element, so let's move up to a group with two elements. That is the cyclic group on two elements. So I'm going to write this as C2, but of course this is the same as, people might write the integers mod 2. Those who've been here for a while, that I don't like writing this, because for me this is the two-adic numbers, which has to do with my research. And we may even talk about applications or uses of p-adic numbers and p-adic integers eventually in the series and their relationships to representation theory. Certainly, I work in representations of p-adic groups, so I would love to make some videos where eventually I talk more about representations of p-adic groups. By the way, I do have some of those videos on my channel already. Certainly, if you search back through some of my live streams, you'll see me yapping about them. But I think I even made like 4 pre-recorded videos about some representation theory of GLN over the p-adics. But we're dealing with we've got a much simpler group in front of us, right? So let's ask ourselves, what kind of representations can we construct for the integers mod 2? Well, representing this as 0 and 1, mod 2, we know, because that we're trying to cook up a group homomorphism here, we know that the identity element of the integers mod 2 must be sent to the identity linear transformation, just id, right? So we're always fixed in that choice. But now we have a second choice here. We need to figure out where we're going to send the element 1. Now, a priori, it may seem, well, our choices are wide open. However, if I look at this, so I'm going to write pi for this homomorphism here. Remember that this has to be a group homomorphism. So what does that mean? That means that, for all elements of our group, I'm going to write it additively now. Pi of g plus h has to be pi of g, and I'm going to write it as multiplicatively on the other side. So this is just because generally for abelian groups, we like to write things additively. For matrices, we like to write things multiplicatively. And this isn't, so this has to hold, this has to be true for all elements g and h of our group. And well, if either of these elements are 0, it doesn't really say very much, right? So if they're both 0, this just becomes the statement that pi 0 is pi 0 times pi 0. But of course, this is true because these are the identity linear transformations, right? Likewise, if g is 1 and h is 0, this becomes a statement that pi 1 is pi 1 times pi 0. But pi 0, I should say composed. I should really be writing composed here, actually, because these are linear transformations. And we're talking about compositions. I'm technically, the way I've written it, we're not talking about matrices yet, but we're definitely going to use matrices to help us out. So we're talking about composing things here, right? So again, of course, this holds. So really the only last condition that needs to be satisfied here, where something significant happens if I take both g and h equal to 1. In this case, this says that pi of 1 plus 1 is equal to pi of 1 composed with pi of 1, right? But that says that pi 1 plus 1 is 0 in this group, which is the identity. So now we get something kind of interesting, right? What does this say? That this linear transformation composed with itself must give us the identity. So in other words, pi 1 as a linear transformation must be its own inverse. And actually, if you think about working through the steps of this proof backwards, we can see that all of the linear transformations are exactly, or all of the representations, I should say, are of this form, right? Because if we had a representation, right? If we had a representation, or rather, okay, we have just shown all of them are of this form, but also this proof shows us that anything of this form is valid, right? So what I'm trying to say is every representation as a homomorphism from C2 into GLV must have the effect where pi 1 is a linear transformation that's its own inverse, and then conversely, any linear transformation that's its own inverse will define a representation of the group C2. Okay, so let's try and make things more concrete, right? Because we did this for an arbitrary vector space now. So in some sense, we've obtained a classification, right? We've obtained a classification like all representations. So what am I trying to say here? If you hand me C2 and you hand me a vector space, I can always construct a representation of C2 on that vector space. And constructing a representation is exactly equivalent to giving a linear transformation, which is its own inverse, right? Applying it to itself as its own inverse. So we have a classification here. But what does this look like concretely? What does this look like for a particular vector space? Well, we have a lot of vector spaces to choose from, right? So we know that finite dimensional vector spaces, so again, let's look at the most simple example. Well, 0 is kind of, we've already looked at 0. Let's at least look, let's look at 1 and 2 and other cases. And then there's also the question of vector spaces are over a field, right? So we could take all sorts of different fields here, right? We could take the real numbers, we could take the complex numbers. We're going to work on the complex numbers, I think, in particular quite a bit, just because the theory turns out to be pretty nice for complex numbers. But there's also, we could be working with p-adics, we could be working with p-adic numbers. We could be working over the rational numbers. This is a really important one that we're going to look at. But what is arguably the easiest field to deal with? Well, I would say the finite fields, and in particular, what's the easiest finite field? That is just F2, right? The field with two elements. So it itself contains 0, 1 with addition and multiplication. So what does that look like then? So now we're going to appeal to one of our other definitions of what it means to be a representation. So we have an equivalent definition where giving a representation, right, is equivalent to defining a homomorphism from your group into n by n matrices over your field. And in particular, this property of being this property of being self-inverse linear transformation, this transfers over in the language of matrices to saying that it's equivalent to choosing a matrix whose square is the identity matrix, right? So, let's consider, we could consider first C2 over a one-dimensional vector space, right? So what is that? GL1. So that is, in other words, a 1-by-1 invertible matrix over the field with two elements. What is that? Well, this is just, right, this is the non-zero elements of the field, because those are exactly for a one-dimensional vector space, the only linear transformations are scalar multiplication, and the only invertible scalar multiplications are the ones which are non-zero, right? All the non-zero ones have an inverse, right? So again, actually, our hand is kind of forced here. So in this case, this is just the trivial group, right? So in this case, in the one-dimensional case, what is the representation given by? We're just sending, of course, 0 and 1 both have to go to the identity in this group, which is 1. Okay. What about bumping this up to GL2? So what is a representation now? So here, this is all 2-by-2 invertible matrices over the field with two elements. And our representation is going to be entirely determined by where we send 1, right? We're going to send 1 to some matrix. And in particular, that matrix had better square to the identity. So all we really need to do in this case is just sort of run through the list of all possible invertible matrices, right? So certainly the identity squares to the identity. That is an option for us. We could take this twisty boy matrix, and let's see what happens when we square it. It will work out to being the identity. So good. Maybe I'll put a little check mark here. Both of those matrices work. And similarly, we can go through and sort of fill in the rest of the matrices and see, well, will this always work? So we could check this matrix as well, see what happens when we square it. So we get, let's see, 1. This will be 1 plus 1, which is 0. This will be 0. This will be 1. Okay, so that works. And so on and so forth, right? I guess maybe I should well, okay, we'll do the complete classification here. So what happens when we square this matrix? Well, we get here 1, we get here 0. 1 plus 1 is 0, 0, and 1. And I think you can see that in this case, actually, it's going to work out that every single matrix. Well, let's check these last ones here just to be safe. I don't want to say something wrong. So let's square these. So this is 1 and 1. Aha! So this one won't work because here we get 0, 1, 1, 0. So this one is going to be out. And this one, it's friend over here. I can't write properly. 0, 1, 1, 1 will also be out for similar reasons. So we have obtained already a complete classification of all of the representations, all of the possible representations for the group, the integers mod 2, over a two-dimensional vector space, right? Two-dimensional vector space over the field with 2 elements. So I think this is where we're going to leave it for today. So next time, what are we going to do? And I encourage you to work on this in the meantime, before the next video comes out. It might not be for a couple weeks. Try and explore, see what you can find out about this. Really try and picture each of these representations, right? This vector space has a finite amount of vectors. So you can really think about what each of these representations looks like. But don't worry, we'll do this together when we come back. So we essentially have a complete classification of these representations. And we can ask ourselves, what are the properties that these representations have? Do they have any similarities? Do they have any differences? What are things that we could ask about these representations? I also plan to, in the next video, we will go on from what we just looked at here to try and extend this, right? Because it now becomes the general problem of really classifying representations of C2 over the field with 2 elements, comes down to classifying matrices which square to the identity over the field with 2 elements. And so there's actually a really interesting way to look at this that's going to use some fun techniques from linear algebra. So with that all being said, let me remind you, I do have a Patreon. If you'd like to support the Patreon, it's $1 a month to just buy me some coffee. It is $5 a month if you would like to join my Discord server. Admittedly, it's pretty dead at the moment, but maybe you could come in and spruce it up. If you want to get a hold of me, I've got my email down below. I'm trying to keep my Your Proofs Are Trash series alive, and in order to keep that alive, I need you to anonymously submit to me your assignments that you want me to basically just grade for you for free on stream, or not on stream, but in a pre-recorded video. So please do that. Let me know if you have any comments down below, and QED.